Hello all, welcome to the project which is estimation of pore pressure using machine learning. So now this is also one of the project in the petrophysics domain. The people who are concerning in the field of petroleum engineering, mining engineering or any of the geophysical related field, this is a very important project for us, and for other people also this can be a very important or interesting project to find out how we can apply the knowledge of machine learning to solve problems of different domains. So during the course of this project, we will learn about pore pressure and its application. Basically, if we are predicting something, if we are finding out, we have to first learn what this thing is. We have to go a little bit in detail. So we'll learn what pore pressure is and then how to use machine learning to estimate pore pressure in the KG basin of India. I'll tell you what the KG basin is and where is it located, and we'll understand more about the KG basin because that will play an important role in our project. So now moving on, let us first understand what is pore pressure. I'm sure that if you all have heard this term during your future classes, that is the high school 11th 12th classes, the pore pressure in geography. Pore pressure refers to the pressure of groundwater held within a soil or rock in gaps between particles. Basically what happens is, if you take out a chunk of soil, okay, so there are certain gaps present in it, there is certain pores presented, and when a liquid or any of the thing gets inside that pore, a gas or liquid gets inside that pore, the pressure which is exerted by the gas on that pore, okay, that is known as pore pressure. That is known as pore pressure. So pore water pressure below the phreatic level of groundwater are measured with piezometers. That is some basic information regarding the units of measurement of pore pressure. And then it is written that vertical pore pressure distribution in aquifers can generally be assumed to be close to hydrostatic. This is basically a term which is concerning the petroleum engineers, or term hydrostatic is mainly used in identifying different things, and which is used by the petroleum engineers itself. Now, pore pressure is observed in many different operations which are performed related to geophysics, drilling or mining, etc. But any of the field, if you go, if it is concerning with earth, it is concerning with drilling, it is concerning with the formation or concerning with the soil, you will come across the term pore pressure. Okay, it is not exactly limited to pore pressure. Okay, consider a sponge. You might have seen a sponge, right? So there are certain pores present in it, and then when you fill the water, when you rub it with water, the water gets inside the pores. So now the pressure which that water is exerting on that pores is known as the pore pressure of that sponge. So this is the same phenomena for a rock. That is, the rock is basically a sponge. It is hard obviously, but it works the same as a sponge. The sponge has porosity, okay, right? So this is the same thing. Now this was all around our, what about pore pressure, a little knowledge, so that what you know what you are doing and what you are doing in the project and what how it will help. Estimation of pore pressure using machine learning can be of grave importance in future perspective. As I said that pore pressure is a very important phenomena when you go for a drilling, when you go for any on-site activity. So if you are able to predict that in future for in present, so it will be a great help in all of the different activities. So and the thing is that we'll be doing the same using the machine learning in the next coming sections. So now I told you that we'll be doing that thing in the KG basin. So first let us have a look of what KG basin is. Krishna Godavari Basin. KG basin stands for Krishna Godavari Basin. Is a pre-cratonic passive margin basin in India. It is spread across more than 50,000 square kilometers in the Krishna River and Godavari River basins near the coast of Andhra Pradesh. So now this is the location of the KG basin, which it is spreaded or it is present in India. It is between the Krishna River and the Godavari River. Okay. So now KG basin is a huge source of fuel reserves to India, involving conventional and unconventional resources. It would be basically the crude oil or the gas which is required to power the nation. Most of the it is the greatest resource of India where all of these things are present. Natural gas production from KG Basin is a key part of India's plan to reduce import dependency by boosting local production. Now, as you all know that the crude oil, which is the natural gas, India is a huge importer. All of these things are imported from outside the world. So now, with the help of KG Basin, we can reduce this. We can increase the production because it contains a huge source of natural gas. So it will help in benefiting. So crude oil production in KG Basin is about 19,190 barrels per day, and natural gas production of 9.8 million metric standard cubic meter per day. Now you can imagine the kind of production or the scale which is happening. So now you know this is I'm telling you to tell the significance of this project. So now the significance of this project, because we'll be estimating pore pressure, and the pore pressure is responsible or will be helping in all of these activities in natural gas extraction, crude oil production, all of these things. Pore pressure is the crucial part. If you are belonging from a petroleum engineering background or mining engineering, you must know it how important the pore pressure is. But all the non-domain, no other domain, non-core guys, I'll tell you that this is I'm telling you to tell you that how important pore pressure is and what is the impact of our project. So now let us understand the basic problem statement. In this project, we will try to predict the pore pressure in the KG basin of India. We have a data set with certain parameters. Basically, we have the data of different wells. Wells is basically the place where you dig to find out to extract oil. The one place which I dig, it is known as that one well. Similarly, we have data of different wells which contains the pore pressure, and with that we'll train our model and we'll find out, we'll try to predict it using different predict the data using different wells. Okay, we'll use that test data to predict the pore pressure. This certain way we'll be able to develop an algorithm, a model which will easily predict the pore pressures inside our data. So we'll be using different ML models and we'll try to compare between them and draw conclusions on which model will perform the best for real life deployment. That means we'll find out, okay, which is the best model for deployment. You can tell that in production to the big companies, right? You can, if you can do, you can contact, you can tell them, okay, this model works the best, and you can just use this and to estimate pore pressure, which will help us in your numerous activities. Okay, and we'll also see different trends in KGFC by visualizing a data. That will be a data analysis part, and you'll see that how we apply data analysis in a particular domain. So now this will be the timeline. First, we'll be doing data analysis. Like the same, we'll be finding out relations, we'll be analyzing the data. Then we'll be doing some feature engineering, that is the data pre-processing part, doing different operations. Then we'll finally build the model. So this will be a very interesting project for all of you. So let's buckle up and move to the next section. Hello all, welcome to our project. In this section, the project is estimation of pore pressure using machine learning. So now in this section, what we'll be doing, we'll be covering the notebook part, or the basically the coding part of how we will implement the machine learning models in estimating our pore pressure, and the data analysis and data processing techniques involved in it. So now I have already told you that in this project we will tell you, try to predict pore pressure using several independent variables with the help of machine learning. Now this is a brief introduction about why pore pressure prediction is important. As it is written, pore pressure prediction is a very important area in oil and gas exploration and production, and it is done in all the basins of the world where exploration wells are drilled for hydrocarbon. So as you know that, as I told you in the earlier in the introduction part, pore pressure is used on a very important phenomena while covering or while drilling for oil and gas exploration. That is the same thing written here. Sudden changes in pore pressure while drilling a well and well stability can cause major problems when one is unprepared. So pore pressure is very important to geophysicists, geologists, petrophysics, and reservoir engineers. These all are the different categories or the type of jobs which were involved in a petroleum engineering domain or petroleum exploration domain. So an accurate pore pressure prediction can help us to reduce drilling risk hazards, to increase wellbore stability, and to optimize casing seat selection, or for mud program design. So as you know that these are the different applications which we can improve or by the estimation of pore pressure, because estimating pore pressure can reduce all of these things, can reduce drilling risk, it can increase the stability and all of those things. Okay, so now you know what is the importance of this project, the idea behind this project, the theory behind this project. Now moving on to the machine learning part, and how we will implement this project. So now the timeline of the project will be, first we'll be importing data and library, then we'll be doing some data analysis, then we'll be moving on to data processing part, then we'll build models, then we'll try to hyper tune our model in order to increase the accuracy. So now I am doing this project in a Jupyter Notebook environment. If you are not familiar with Jupyter Notebook, it is an IDE just like any other IDE which is used for coding, but Jupyter Notebook is basically for data science and machine learning practices. Now, if you're not familiar with it or you're not comfortable with it, you can either use Google Colab. That is a server which runs in your online environment. This is a server which runs in your local environment. So if your computer specs are not that good, or if you think that it is lagging, so you can always use Google Colab. It is free of cost and it is provided by Google. The difference is that the servers, the CPU and GPU provided there is of Google, which is of online, so the performance will not lag, and it basically will run on internet. So you only need to have a good internet connection for it, and rest of the things are same. Implementation thing, each and everything is same. So there is no difference between as such in Google Colab or Jupyter environment. So now the very first thing is we'll be importing the libraries. So what I'm saying, I have imported pandas, numpy, matplotlib, seaborn, and different magic line, which this line will do, it will keep the figures in the notebook itself. So now these are the libraries which are used for data visualization and data processing. So you all must be familiar with these libraries: the pandas, the numpy, the matplotlib, and the seaborn. Okay, so now the next thing which we'll be doing is reading the data. So now, as I said, that we'll be having different well data. So here we have different data, well 1 to well 8. There are 8 wells which we have the data, for which we'll be using the first 6 wells to train our model, and then the next 2 wells to test our model. Okay, so now you know how these things works. Okay, I'll be providing you with the whole data, don't worry. Then what I'll do, I'll just concatenate this whole data into one single data frame called df. Now when I'll see the shape, then I'll see that okay, there are around 11,944 rows. Okay, there are this much amount of data present of these total 8 wells, and there are 10 different columns. If I want to see my data, so now this is my data. It has a column called depth, because which means that at particular depth these are the values which are recorded. The one is the gr log, that is the gamma ray log which is present, and another one is density log. VPs, the velocity, P wave velocity, this is shale content, this is one of the log. Porosity, resistivity, stress, and finally our independent feature, pore pressure. These are some of the core terms which you can study, or it is not that necessary to study, because you will be analyzing the data and you can find out, or you can see out the different domain knowledges, the domain knowledge on your own. If you are that interested, you can google these things and you can find out, okay, what are these things and what are these things important for. But when we'll be doing data analysis, we'll automatically find out how are these things correlated, and which of the following is important and which are not. So this was our whole data imported data import of data and libraries part. So now from the next section we start doing the data analysis part, where what we'll do, we'll find out different relations and we'll see how our data is arranged in the kg basin. Remember, the data this is present is of kg basin, right? This is the data of kg basin. So this is the whole data. And now in the next section we'll be doing the data analysis, finding out details, and the building models, which will be pretty interesting. So let's proceed. Hello, welcome to the next section of this project. In this section, we'll be doing the data analysis part. So now, in the previous sections, we have seen the data, we have understood the problem. Now the next part is doing the data analysis and building our models. So now the very first thing which comes in our mind while doing our data science project is in the data analysis domain is finding out the null values, whether our data set contains any null values or not. So now this was the data which I told you, which has the different attributes, which are the independent variables, and this is my dependent variable, pore pressure. Now moving on, we named this data frame as df, okay, if you remember, and the shape of this data set was around 11,500 494 rows and 10 columns. So now the moving on to finding out is there any null values or not. So now as you can see, there are no null values in our data set. So which is a pretty good thing, because otherwise we'll have to perform several different operations to finding out the null values, but there are no null values in this. So moving on, outliers. So now outliers are a very big thing. Outliers can be a problem when you are building a model, because the thing is, when you try to build a model, if the model contains several outliers, the model will get biased. Okay, the model will get biased and will not be generalized to the kind of data which it is used to. Now, then when you'll try to fit another data, it will have different outliers. So the model will get confused and will eventually result in a bad prediction. So it is very necessary to find out the outliers. Now for this section, what we'll do, I'm finding out the different columns. The very effective way of finding out the outliers is using a box plot. What a box plot will do, it will tell you all these statistical details in a chart of graph, and it will give you little small dots in the form of outliers. You will see what I did is here I used I found out all the columns, then I prepared that and stored them in a list. Then I'm saying for calls in columns, I'm carrying out each of this value, and I'm plotting a box plot for it. I am plotting a box plot for it. Now, as you can see, the box plot for all these things are plotted. Now, as you can see, this is the 75th percentile, my 50th percentile, 25th percentile. This is my maximum value. This is my minimum value. I hope you know how to read a box plot. So now the black lines which are present are these are our outliers. Okay, these are our outliers. So now, as you can see, there are several number of outliers. Many number of outliers are present. Okay, so now what we have to do, we have to remove them. So now what we can do, we can write our logic. We can write our logic which will tell us okay how many outliers can remove. So by seeing that graph, what you can we can do is we can limit the data to that. Okay, for example, in the help of in this scene of caliper log, what I'll do, I'll say okay, limit my data with the values greater less than 12 only, and rest of all are non values. Okay, rest of all keep it as non values, because these are outliers and they will delimit my system, they will delimit my model, they will destabilize my model. Remove all those values and keep the value till that. As you know that there are very small number of values, a number of points, so our data will not, our model will not that get that much affected. So what we'll do, we'll just use the column. Okay, this is I say I plotted here in the, I just plotted it here, I just plotted it in a single figure. Here there was in a different figure. How you can do this, you can always use a subplot model. What it will do, it will plot out a big figure, it will plot a big figure 1310. I plotted a big figure, then I told you okay, plot subplots. Okay, and gave the different decision, three row like the three rows, two columns, like that, and the first position, second position, third, fourth, fifth. That is pretty simple. Okay, so now moving on, what what I am doing is I am using the same thing. I am using the same thing which I told earlier in the gamma array. If you'll see in the gamma array log, I am limiting my value which is less than 70. I am telling you okay, all those values which are less than 70, put them as non-values. So what this will do, it will remove all these outliers, where all our outliers will be removed and they will be converted into a non-value. And the same thing which is happening for the density RHOB. Now the very important factor here is in the VP and VSH column. So now as when you see the value which somewhere it is present here minus 1000. Okay, and here it is 45. So these are a very major outlier which are creating a problem for us. So what we'll be doing, we are limiting our values to 1.70 and 0.37. VP 1.70. Okay, to limit here till here only. I don't want the values greater than that, means this value will be removed or converted into a non-value. So now move similarly all of those different features are there. Now what I am doing, I am just dropping all the non values. Here we converted all the values, now we are dropping all the non values. So now when I'll see the box plot, you can see the huge difference here. So now as you can see the difference, okay, all of the non value, we have only kept a few values, we have only kept a few values, so that because they are very close to 100 and 0th percentile, so they may not create that much difference. Again, if you want to try out testing a model, you have to find out different approaches. This is one single approach to remove the outliers. There are several other, which is, this is basically the IQR approach, that is the interquartile range approach, in which we found out the 75th percent, the 100th percentile, 0th percentile, 50th percentile, then we'll remove the data which is present outside that range. Now there are different several algorithms like the one class SPM or the outlier removal techniques. There are different models which will do the same work. You can also apply those models and see. So see, basically doing a data science project is not being of doing only one single technique. This is only for the case sake of demonstration to teach you how these things are done, because but this is not the only method, right? You can perform all the different operations, all the different things in a single data set. Even in the same data set you can apply any other outlier technique and see what is the change in the accuracy, how our model is performing. So this is how a data science domain project is done. So this is basically the basic idea how you can perform it. Okay, so now, and we have removed our outliers. Now let's see what is our data set. So as you can see, for earlier our data set was around 11,500 data points. Now the left is 10,408 rows. So as you can see, not much data is lost, around only 5 to 6% data is lost, so that is bearable. Now but in a position where you are in a position where a lot of amount, say 20 to 30% data is lost, so it is basically better to not do the outlier removal and to think of something else to carry out with your problem. Okay, because that will result in a lot of outlier data. What you can do, you can convert those outlier data into nans, and instead of removing those nans, you can replace those nans with another approach, like using a mean imputation, random sample imputation, any of those things. So now if you want to, so this was our whole data outlier removal part. So this also comes under the data pre-processing technique, but I have included it in the data analysis part only because where here we understood all the different things and we also observed some of the data. So that's why I have listed it here only. So now in the next section, what we'll be doing, we'll be scaling our data down and we'll be seeing how our data is distributed and how we can scale down to it to a proper level in the next section. Hello all, welcome to the next section of this project. So now in the previous sections we have understood about the problem statement, we have had an introduction about the statement, we understood about our data, we did some data analysis, in that we removed the all of the outliers. So now in this section we'll be basically doing the data pre-processing, or more of the continuation of the previous thing which we are doing. So now in the previous section we saw that we removed all the outliers which were present. So now after that we observed that there are around 10,408 rows that are present. So now if we plot a distribution plot of these columns, okay, these are all the different columns where only the pore pressure and depth are removed, because pore pressure is our dependent variable, sorry, dependent variable, and it is as it is. So let us see that how our independent variables are distributed. I am plotting a distribution plot which comes under the name of sns.displot, that is the Seaborn library. What it will do, it will plot a distribution plot for all of these. So now as you can see, the count is there and the distribution is there. Now as you can see, our data, this doesn't look good, right? This doesn't not at all good look. This is because of the thing that our data is not that much good distributed, not that much distributed easily. So now what we'll do, we'll just use a scaling technique in order to scale our data into a common format, into a particular format. You can either use min max scaler or standard scaler. These are the normalization techniques, and these techniques are very much important when you are dealing with a regression problem. Okay, these techniques are very much important when you're dealing with a regression problem, because you are dealing with the data, and if the data is not in a particular scale or not scaled down, it will be a problem for your model, because it will get confused. Because one of the feature will be have on the value of very high, and another feature will have a value in the range, a completely different range. That will be a problem. So what we'll be doing, will be scaling the data in the value of 0 to 1. That is known as min max scaler. This technique is known as min max scaler, which will just scale my data in between 0 to 1. Another technique is standard scaler, which will basically works on the z-score value. It will basically scale your data on the basis of your mean and median. Okay, mean of your data. It will scale on that. You can perform that also and see what are the different things which are by happening in your data frame, in your accuracy, or how your model is performing. Here I have used min max scaler. That's a simple thing. You can introduce, you download it using the, oh, you can import it using the sklearn pre-processing library. Import min max scaler. I'm defining my columns. I'm saying, okay, fit transform scale dot fit transform. What it will do, it will automatically fit all the data and transform it into 0 to 1. And I am just creating our data because these are the things, this will be in a list. I'm converting this into our data frame and yeah, saying, okay, take columns from these columns which I have given. Okay, so now I have done this. I'll just do the reset index because the index will get mixed up. You always create a data frame, do the reset index so that the index will not get mixed up. Now this is my scale here. Now how perfectly my data has become. It is converted into 0 to 1. See the magic of the scaling. Earlier our data was around very much disturbed, but now it is completely scaled. But now this data is not containing the pore pressure because earlier we didn't scale our pore pressure data. So now what we'll do, we'll just merge that data into it. As you can see, our pore pressure is also with us. Now what we'll do, we'll just say, now what we'll do, we'll just use the distribution plot to find out. Earlier you saw that was your distribution plot, right? So now in this section you see how our distribution plot has changed. Now the values are only converted between 0 to 1. The only difference is this VP value. This is because the VP value has not changed much in our data. It has not changed much. So the most of the values are lying near 1. That is why the count is that much high. And all of these are perfectly normally distributed. So this is how beautifully our data has been written. So now the next thing is what we'll do. We'll just find out different things. Then we will find out the relations, like how our data or our pore pressure, that is the dependent variable, is related to all these different independent variables. Like this, I have plotted a joint plot which will create a scatter plot and a line plot and a distribution plot all along with the same in the same graph, and it will tell you me that how our relation is this. Now when you'll see that after in increasing the porosity, in after with as the porosity is increasing, my pore pressure is decreasing. As you can see, the line is down, and you can also observe from the scatter plot. Similarly, I can do this with the same density plot. My density feature, this is my porosity, this is one of my feature, and another one is my density. It is exactly the opposite. When you see the density is increasing, the pore pressure is also increasing. That means it is positively correlated. Okay, so now what we'll do now, as you saw that the VP was creating a problem because that the all the values are same, right? Most of the so this may create a problem for a model, or this may not create, or this may not benefit us more. The another way of checking is we can also check the correlation, but by seeing the data only we are seeing that okay, this is not that much of importance because all the values are same. Okay, so we can just simply drop it. If you don't want, you can not, you can leave it, also. Okay, so now I have dropped the VP. It's your choice. You want to experiment it, this is your project. You can do it with the VP and see what are the results. With my understanding, I have just dropped the VP. So now when I'll plot a heat map of the correlation, this is my heat map. Okay, so now basically a heat map which is present in a Seaborn library. Under that, I have given the letter df dot correlation, and now if I write alone df dot correlation, so this is my correlation data frame. Okay, I have just converted this into a visualization format. So how beautifully it is converted. So now as you can see, the color scheme is representing my correlation. This is my pore pressure, which is seeing that stress is highly correlated. Resistivity is also highly correlated positively, whereas the porosity and caliper log are highly correlated negatively. That means if the value will increase, it will the pore pressure values decrease. Similarly, all of these things are there. So now this is the all our data analysis and pre-processing part. The next thing which is left is our model development. We'll finally build the model. we finally build the model. In that, what we'll be doing, we'll be splitting the data, we'll be carrying out these different models, and all of these things will be hyper tuning the models and see the results. Okay, so let's proceed to the next section. Hello all and welcome to the next section of our project. So now finally we have done the data analysis part, we have done the data pre-processing part, and we have prepared our data to get ready into the model. So now previously we saw the correlation matrix. This is right here. We scaled the data to 0 to 1. We saw different relations between the data. So now the time is to build our model. So now to build our model, we first need to split our data. We have to split our data into train and test data. With the training data, we shall use the data for training the model, and testing the model. We'll be using it to test the model, how our model has performed. Now, the very first thing is we'll be converting or splitting our data into dependent and independent features. So now the X will be marked for independent features, independent variables. Okay, so now this and this is my dependent dependent variable. Sorry, dependent variable. So now I've included the depth also, because depth also plays no major importance in prediction. Because as you can see with the logic, why I need depth in order to predict, right? Depth is certainly a measure. It is not that a measure to find out, okay, what is the different thing. Okay, depth is not that important. So now moving on, the pore pressure is my dependent variable. The pore pressure is my dependent variable. So now in the next thing, what I'll do, I'll just use the train test split, where I'll see this is my X, that is my independent, and this is my Y, that is my dependent variable. And the test side is 0.1. You can, okay, let's do this 0.2. That means the 20% is used for training data or test data, and 80% is used for testing data, training data. Sorry, 80% is used for training data and 20% is used as testing data. So now when I see the training and testing size, the training size is around 8,326 rows, and the training data is 2,882. That means we'll be testing our model in these 2,082 points. Okay, so now moving forward, see what are the different models which we'll be using. We'll be using linear regression, random forest, XGB regressor, SVM regressor, ANN. I'll be telling you a little about this. The very first is linear regression. So as you all know, multiple linear regression is the simplest model which can be used in the field of machine learning, that works on a simple gradient descent formula, and the very important very it comes under the sklearn.linear model library. What I'll do, I'll just import it. I'll say, okay, linear regression fit intercept is equals to true. I'll fit my model. I'll just use predict my model. Then I'll find out what is the score of my model by using the X train and Y train. Okay, my training score and testing score. As you can see, my training score is 66%, testing score is also 66%. So now you see this is not a very much good score, right? 66%. No, that is not a good score. So moving on, if you want to see the coefficients and the intercept, as you know that the linear regression works on a straight line, y is equals to mx plus c, right? So these are the different slopes. Y is equals to m1x plus m2x plus m3x, and as we have this 7 features, right? 1 2 3 4 5 6 7 7 features we had, so we had 7 different slopes. For each feature a different slope is there. Okay, and we have one intercept, that is the c. Y is equals to mx plus c. So this is one that intercept. Okay, so this is for you to make a regression line. Okay, so now if you want to see the distribution or the joint plot of how your data is distributed, that means one is the prediction value and one is your original value, that is the y test value. So this is how it is, that as you see it is much scattered, as you all know that the accuracy around 66% only. So what can you expect from it? So now let us see how let us see how our multiple regression model will perform. Previously, let's see what is the score. The R score is around 0.66, MAE is 93, RMSE score is 120, and MA mean squared error is this. This is a little short program which tells us the accuracy, tells us the import. That means the R square, MAE, mean absolute error, mean squared error, MSE. And then what I'm just doing, I'm just appending and I'm just storing this all of these things in a list. Okay, in a list, then I'm just converting it into a data frame. It is a pretty simple code. If you'll have a look at it, you'll get it. So now moving on to ridge regression. Ridge regression is also a type of linear regression model. Only the thing is a little difference is in the cost function of that. A little parameter is involved which is known as alpha. Y is equals to mx plus the cost function alpha is added, which what it will do, it will try to reduce the overfitting of the model. Okay, now we have chosen here alpha. Alpha is generally a very smaller value. Here I have chosen 0.001, but as you can see, it is also not that much effective as the accuracy is same, which means that our regression model is performing not that good. So similarly, using the same accuracy metrics or the finding out all of these things. So now what we'll do, we'll just find out the plot for this y test and y prediction value. That is the prediction and the true value. Okay, so this is the scatter plot. This is similarly the same as it is, because obviously it has the same accuracy and it also didn't perform that much well. Now moving on, the second model we have random forest regression model. As you know, random forest is basically a bagging technique in which what we do is we create different decision trees and we predict the prediction from all of that, and then we come out to a common prediction which has the largest number of votes. Now, if you want to go in a little bit detail of random forest regression, you can always check out the documentation of it. Here, we will not discuss that in detail. We'll just implement the model. Random forest regressor will just predict it and we'll see, okay, what is the score or what is the accuracy score. Okay, as you can see, the R score is around 95%. As you know how good a random forest model has performed. Okay, adjusted R score is 95 and R score is also 95%. Okay, so now if you want to see the scatter plot between it, now as you can see, it is in a single line. Okay, as you can understand how good a model is performed. Previously, if you compare it, the scatter plot from this to this, how good they are, how good the scatter plot is, as we have an accuracy of very good accuracy of 0.95, that is the 95%. Moving on, that is the xg boost. Now xg boost is extreme gradient boosting. Now this was a bagging technique in which we create different models in the form of decision trees in the case of random forest, and we take the prediction from all of them, then the prediction which is having the highest number of votes is selected. So now moving on to the boosting model, XGB, extreme gradient boosting. In this, what we do, we create first a base model, then we try to improve that model on the basis of our prediction. That is what the XGB model does. So now also again you can see its documentation to kind of have a foolproof explanation for it. So now moving on, we'll just fit our model, filter, strain, understand that we are not doing the hyperparameter here. We'll do that in the next section. We'll just implementing our models and finding out which model is performing the best. We'll just predict it, then we'll find out what is the accuracy. As you can see, it is also the same as the random forest model. The R score is around 95%. Adjusted R score is a little bit decreased than 93%. If you want to draw a scatter plot, this is the scatter plot for it, predicted versus actual. As this is a very simple command, right? I'm just using the plt.scatter command to find out the scatter plot. The next model is SVM regressor model. Now the SVM is generally a model which is said to perform very well in the regression techniques. So let's find out how does it perform. So now I'm just fitting my model now, as you can see. Okay, now as you can see, my model has not performed that well. It is performed the same as the regression model, the linear regression model. So now what we understood it here, that you can't generalize something on the basis of that model. Like if you said SVM always perform better. So now as you can see in front of you, SVM has performed poorly, very poorly in comparison to XGB and the random forest. So you can't really tell which model will perform the best. You have to check it out. You have to do the trial and error method. You have to try out different models. Then you'll come to find out, okay, which model is performing the best. In that case, it only depends on the data, and the data that, okay, the model has not performed well, that's why I'm using the SVM regressor. It is a typo error. It should be the fourth model, because this is a fourth model, and this is a scatter plot. As you can see how scattered it is. It is not that good because the predictions are not good. Now the last model is we are using the neural networks. Okay, so now in the neural networks, what we are doing, I'm using TensorFlow. As you all must be familiar with the TensorFlow library, which is used for the neural networks. I'm just using three different layers for my model. I'm just using three different layers for my model. Okay, so now I'm using a sequential model. Sequential model, if you might have heard about sequential model, is a model which has different layers in it. Okay, the layers which I am adding is the first layer is the ReLU. I am using all the activation function is the ReLU function. Okay, I am using all the activation function ReLU function. The first layer is this, the model input layer. Input dimension is 7 because, as you know, the seventh there are 7 features that is why the dimension is 7. Another layer is the another dense layer which have around 100 neurons, then 50, then 25. Activation function is ReLU. Then I'm just compiling it all on the basis of mean squared error. That means our evaluation will be done on the mean squared error. This is my loss value. Okay, this is my loss value. I'm just saying, okay, empty.fit. I'm just passing all my features in the form of arrays, and I'm saying, okay, put the epochs is 100 and batch size is 10. Now if you want, you can also decrease the number of epochs. Okay, decrease the number of epochs, but here I have done the 100 epochs only. Now it will take a lot of time because it will just iterate through all of those things in 100 epochs. Then we'll see what is the difference. But as you can see, our lost function started with a value of 11 lakh 58,000. Now it decreased to 20,000. Now it is decreasing more and more, and the main purpose is to decrease our loss model, right? To decrease our loss model. So now this was the whole function. By the time it gets executed, it will take a little time to get executed and predict the model. So now in the by the time it gets executed, we see that we have created around 5 models. Okay, the one is the S, that should be 4. One is the SVM regressor, XGB regressor, random forest, and the linear regression, and last one is the neural network. And we have seen that how these models have performed. Now in the next section, what we'll do, we'll just carry out the top 3 models. We'll just take 3 top models and we'll hyper tune it and we'll see the results. Okay, so now we'll see the this also in the next section by the time it will get executed. So now as you can see, we'll just predict it, and we also find out what is the accuracy, and all of these things we'll do the hyper tuning. We'll be doing our final predictions in the last and the finals. Hello all, and welcome to the next and final section of this project. So now previously we have seen that how we have built different models, and we have seen that what are the different trends of our data and what are the different parameters which we did earlier. Now we have seen that we use 5 different models, that was random forest, XGBoost, neural networks, logistic and regression, and support vector machines. So now in this, the top 3 performing models were random forest, XGBoost, and ANN. So now what we'll do, we'll just hyper tune these top models, and then we'll see if we have some increase in the accuracy or not. For this, I am using randomized search CV. Now you can also use grid search CV. They both are used for hyperparameter tuning. What grid search CV does is grid search CV searches the parameters in a pattern, right? And the randomized search CV is random. It search all the different parameters with all the combinations. So when dealing with a very large amount of data, it is very possible likely to use grid search CV, because it may take a huge amount of time if you have data of lakhs and lakhs. But here we are having data in thousands, so it is very feasible to use randomized search CV. I'll just define it. I'm just using this command pprint. With the help of pprint, you can get all the parameters which are present in a library with a winner model. Like I am using rf.get params, it is giving me all the parameters. So now in the very next thing is I am using these parameters to create different level of options like bootstrap, true, false, max step. I said use check these, then max feature, then minimum sample leaf. I am using all of these things. I am just saying that okay, then I'm defining this. Estimator is random forest, parameter grid is random grid, the dictionary which I created. Then I'm saying number of iterations is 10, cross validation score is 3, and all of these things. So now I'm not fitting the model here because it may take a huge amount of time, because it may take a time, not huge amount, but it may take 5 to 10 minutes, or basically the 5 minutes if you have a good machine. So now you just have to write rf random dot best parameters. It will give you the best parameters. In my case, these were the parameters which I obtained. I am just defining my model on the based of these. I am just fitting my model with that. I'm just fitting my model. Then I'll see that okay, what is the accuracy with those models. Now the thing you we have to understand it first. What we did, we created a model, we checked out different models. Then we'll see that okay, I got the best accuracy in these models. Now what I'll do, in order to increase the maximum accuracy, I'll just hyper tune these models with the best parameters possible. It may be possible that there may be some of the parameters which will be left because the model that got fitted was with the basic parameters. It may be possible that some of the parameters will be more accurate, will be more proficient in predicting my results. So these were the parameters which I obtained, although most of the parameters are default here only, so this may not get a huge difference in our accuracy. As you'll see, we have fitted the model. We'll just predict it, we'll just predict it, and then we'll see. We'll Okay, sorry, I just created it again, then we'll have to fit it again. Now the thing is, then when you see, we'll have an accuracy for this. Now the next thing which I did is I created a depth variable, because earlier I removed the depth. Now in order to visualize this pore pressure on the scale of depth, because how will the pore pressure increase decrease? It is based on the depth. It is this depth the pore pressure was this, at certain depth the pore pressure was this. I am creating a depth column to visualize my pore pressure data. I am creating sometime random variable between 30 to 300 with a length of x text, and then I'm just saying okay, create a new column with it, and just see and then we'll just see and compare with the actual and predicted variable. Now as you can see, if I see here, the accuracy is 0.95. As I said earlier, because the things which were selected were the basic only, no, that means our model was performing very the best with the base parameters which are already present. No other things were needed. Now I'm just saying I'm creating a random forest, I'm creating a depth column and just saying okay, plot this column. Now this is the simple program which I wrote. I just appended my predicted PP column and just say okay, plot this column in the single plot with a predicted PP and actual PP. You can also change the color if you want to do this red. You can do this red. Okay, this is the red. Now red and blue. Red stands for original, blue stands for predicted. As you see, it is overlapping. That means our data is predicted very good. Now the next thing is I am just plotting a R square graph. Now this is the R square graph scatter plot, which giving me scatter plot in true and predicted value with the R square value. So now the next thing you can also do is you can use the cross validation score to find out a total mean using the k-fold different validation scores. Now I'm not doing this here because it may take a lot of huge amount of time. Also this is particularly good when we have a overfitting case, but here we don't have any overfitting case as such, so we'll just skip this around. If you want, you can do this, you can find out the total R square. Moving on to the XGB model, I'll just do the same thing. I'll just find out the PP print library. These are the different parameters. On the basis of that, I arrange different parameters and stored it in a dictionary called params. Then I'm just saying okay, plot this model, use this and find out okay, I'll just the okay and find out okay, what are the different things present. Okay, it will get just fit. Then I'll say okay, what are the best parameters? Now the best parameter which I get will be these different parameters. These are the parameters. Also now what I'll do, I'll just fit my model. This is the model which it got fitted. It got fitted with these models. Now I'll just store it in the model named pred xtune and just predict the same. Now as you can see, I am getting an accuracy around 0.94%. Earlier we got an accuracy of around the same, actually 93. We had an increase of 1%. Okay, that is not much difference. We had only an increase of 1% in our accuracy. So as you can see, in both of the models, hyperparameters tuning was not that much required because it was the same. The thing is the same. We are getting the same accuracy. That means our model is performing well with the base parameters only. Now the same thing, I'm just plot these results. As you can see, the the red is for original, blue is for predicted. It is identical because though both of them are performing the same. Now this is the scatter plot with it. The same thing, the k-fold cross validation which you can do. Again, I'm not doing it because it may take a huge amount of time, because it will get around with the different folds with around 10,000 of data. So it will require time. If you want, you can do this. Now the next thing which I did was I used a PyCaret library. What a PyCat library, it is basically an automated machine learning library. What it does, it does all the model development work for us, but it will compare all the different models, and then it will find out, okay, which is the best model. Then we'll fit our model with the help of that. Okay, this is a very simple library to use. I am just giving my df. I didn't have to split the data. I just give my df, and I'll say, okay, data is equal to df. Target is my pp, that is the pore pressure dependent variable. I'll just say normalize is equal to true. It is normalize the value for me. Remove outliers is equals to true. It will remove all the outliers. Profile is equals to true. It will give me an overview of the profile, like what is the overview, how are my variable distributed, all of these things. This is basically for people who don't have much knowledge of data science. If you want to excel more in what is the automated machine learning libraries, there is a course for automated machine learning libraries in a book. You can check that out, course for the developing machine learning models using automated machine learning library. Now when I'll compare the models, it will again take time. That's why I'm not doing that. Well, you can do that on your own. You just have to run these commands. Now it will say et create model. The extra t regression was the best model which was created. Okay, the best model which was created. It will say, okay, then we'll do the same thing. We'll find out the predictions and we'll plot the results. So now the another thing which I gained about was the results. Now we have done all of those things. The finally we gave out a 96% accuracy was obtained by random forest model, followed by XGB regression model, and then SVM model. So this was the whole notebook present. You can use this notebook and you can find out different results, when see obtain different results, check or experiment with different parameters and all of these things. This notebook will be provided to you along with all the data with it, so you can check it out and have fun and try it out yourself. Thank you.